All right, so we've been doing rational numbers. Now we're going to do irrational numbers. And the first thing I think about when I hear the word irrational is I think of an emotion. When you think of somebody that's irrational, what do you guys think of?
Crazy, out of control.
Crazy and out of control.
Don't listen to anybody else's opinion.
Don't listen to anybody. They're kind of random. Okay? So that's the same kind of thing you got to think of when you think of numbers that are irrational. They're numbers whose decimals don't terminate. They go on forever and ever and ever. And they're decimals that don't repeat. Okay? Yes, this is the definition of irrational numbers. I'll deal with that in a few minutes. Okay, so an example of that would be the square root of 2. And notice that it has 1.414214, blah, blah, blah. It goes on forever. It's random. Pi is the same way. Okay, so those are examples of irrational numbers. Some examples of rational numbers are like 3/4, 0.625. Notice it stops. -5.3 repeating would be a non-example. A little bit of terminology for you. When you see this with a hook in front of it, it's like a division symbol with a hook, that is the radical sign. And the number on the inside is called the radicand. Okay, this some terminology for you. Principal square root is the positive number that is multiplied by itself to get to the radicand. Okay, so the square root of 36 is 6. So that is 6 is called the principal square root. So a perfect square is a number that has a good principal square root that has no decimals, right? So the square root of 36 is 6. Yeah, these are examples. And for there's two ways in which we will go about solving a radical. And one of them implies that you need to know perfect squares. The other one you don't. You look at this number right here. If you have a number, you can divide it into two numbers. You can take the square root of one times the square root of the other. The other way to think of this would be square root of a times the square root of b equals the square root of a times b. I'm not sure why it was written this way, but it works both ways. Okay? So, for instance, if I have square root of 5 times the square root of 3, that's the same thing as saying square root of 5 times 3, which is the same as saying square root of 15. Okay? Now, to think of it backwards, you can actually simplify a square root. So, this is where I'm asking you to think about these perfect square roots. What perfect square goes into 75? From the chart that you just wrote down. So 25, yeah. So the perfect square of 25 goes into this 3 times, right? So now I can simplify that because I could take the square root of 25, and that would be 5 square roots of 3. Pardon me? Yeah, this is just, it's simplified.
So what's on the other side of the variance?
On this, I was just showing how you could take 2 square roots of a number and then multiply them and end up with a total. So one way is this, by going this way, we're simplifying. But going this way right here, we're actually just multiplying. Okay? I have more examples. So, down here below, we have square root of 7, and this should be, it's not really a square, a square there. It should be a times. Okay? So a square root of 7 times the square root of 7 is what? Yep, it's the square root of 49, which happens to be what? 7. So here's something you should know. If you have two square roots of the same number, it's just going to be itself without the square root. Okay? So for instance, the square root of 9 times the square root of 9 is what?
9.
Yep. Okay? The square root of x times the square root of x. It's just x. Right? Now on the second one, we have square root of 6 times the square root of 12. So that's going to be the same thing as the square root of 72. Now, I want to ask you guys, what perfect square goes into 72? Nope, 12 is not a perfect square. 6 is not a perfect square.
15.
Remember the chart from above.
8. 9.
9. 9 is a perfect square. Okay? So this will be 9 times 8, right? There is actually a larger perfect square than that. Bigger than that. Nope, 21 is not a perfect square.
24.
You guys look at your chart.
37.
36. 36 times 2. Okay? This is the chart I'm talking about that we just copied a few minutes ago. That one.
You copied this chart?
Yeah.
It's so much to write. Imagine.
Okay.
I know that on the top of my head.
All right. So, this is the easier. You take the largest one you can find. So, then I can make this into square root of 36 times the square root of 2, which is 6 square roots of 2. Okay, that is the old way of simplifying this.
I like that one.
I want to show you a different way of simplifying it, because what you can do is actually take the number 72 and find its prime numbers. What are they? We know 9 and 8 go into it. We're doing a factor tree. 3 and 3. What goes into 8? 2 and 4. 2 and 2. Okay, so if I take the square root of 72, it's the same thing as saying 2 times 2 times 2 times 3 times 3. Now, what I want to do is find pairs of numbers. How many pairs of 2's do I have? 1. I can take out 1 pair. And I can take out 1 pair of 3's. So I can actually write this as 2 times 3 because I'm taking them out of the square root. I'm leaving this one behind because it doesn't have a pair. 2 times 3 is what? 6. So 6 square roots of 2. See? This way is a little bit easier because then you don't have to have your perfect square chart memorized.
What way would you recommend though, just because one's like basics and one's like basics?
I like doing the second way because actually this way works well when you're doing third roots and fourth roots too. Okay? So like if I have the third root, of, say, 24. So let's find out what all my factors of 24 are. We got 2 and 12, 2 and 6, 2 and 3. Correct? So when we're doing a third root, we're looking for triplets. So I have 1 triplet right here, so I can take out a 2. So I just find it's really nice and handy to use for different types of roots besides square root. Because, I mean, who's going to memorize perfect triplets or perfect quadruplets? Yeah? See how much? Okay, so what goes into 12? 6 and 2, 2 and 3. So I can call this 2 times 2 times 3 Do I have a pair of anything? 2's. So I can call this 2 square root of 3. Does anything go into 17? No. It just stays the same. No, not possible to simplify.
So like, that was on the test, we should just say not possible.
Yep. So if this was on the test, you would just say not possible. Or already simplified. Okay, so 48. 8 and 6. What else? 2 and 4. 2 and 2. How about 6? So now I can rewrite this as 2 times 2 times 2 times 2 times 3. I have 2 pairs of 2's. So that will be 2 times 2, I'm taking out, square root of 3. 4 square roots of 3. See, isn't this fun? I love it. Okay, what goes into 98? 2 and 49. And 7 and 7. So this would be the same as saying 2 times 7 times 7. We have a pair of 7's. So 7 square roots of 2. Sure. So 25 and 3. So that would be 5 and 5. So we have 3 times 5 times 5. A pair of 5's. 5 square roots of 3. Okay? How about 27? 9 and 3. Okay, so now this one we have 3 3's. How many pairs do I have though? I only have 1 pair, so I have to leave 1 3 underneath the radical. Can only take out the pair. Cool? Quotient rule for square roots. It's the same thing as taking 2 numbers and dividing it. So for instance, if I have, let's see here, square root of 100 over the square root of 25. That's the same thing as saying the square root of 100 divided by 25, which is the square root of 4, which happens to be 2. Okay? Okay, so on this one, we do the same thing. Square root of 80 divided by square root of 5. And we put it both underneath the radical. 80 divided by 5 is 16, and the square root of 16 is 4. For part B, it's not so simple because what happens is you get 90 divided by 2, which is 45. 45 needs to be simplified. So we broke it down into 5, 3, and 3. Have a pair of 3's, so we take out a 3.